Hello, in this video, we're going to be talking about drag and air resistance. So drag is a force that depends on the velocity or the speed that an object is traveling, and it acts in the opposite direction of the motion of that particle. So what this force exactly is a bit complicated. So it depends on the shape of the object. It depends on the nature of the medium, the interaction between the medium and the object, and so on and so forth. So to get a better handle on it generically, we can do this tried and true trick. We just Taylor expand um, this force. We've got something that now is based on powers of velocity. And we'll keep the lowest two terms for now. So we've got a linear term and a quadratic term. And so these terms are each have a proportionality constant. So the linear term is b times v, and the quadratic term is c times v. So from dimensional analysis, we can say that B is dependent on the diameter of the object and D is dependent on the diameter squared of an object. I mean, they just have to be lengths, but diameter or radius or something like that are nice length scales. So based on this dimensional analysis, if I were to look at the ratio between the quadratic drag and the linear drag, I end up with something that's a constant. So this is dependent on the medium. So this is 1.6 times 10 to the 3 for air at standard temperature and pressure times the diameter times the velocity. So I can look at this for a bunch of different cases. So, for instance, a baseball that is 7 centimeters in diameter, traveling at 5 meters a second, has a ratio of quadratic to linear of about 600. So, this is strongly in the quadratic regime. If I were to look at a sneeze, for instance, the droplets leaving my nose are approximately 5 microns, and they're traveling really fast. They're traveling at 50 meters per second. And if I plug these in, I end up with a ratio of quadratic to linear of about 0.5. So this is saying that both quadratic and linear forces are approximately equal since this is of order 1. If, on the other hand, I were to look at bacteria, assuming that these bacteria lived in air, they have a diameter of 2 microns and they travel at 30 microns a second. And so this gives me a ratio of quadratic to linear of something like 10 to the minus 7th. So this would be a strongly linear behavior. So in this case, quadratic completely is irrelevant. So we can use these estimates to tell us what kind of drag we need to use in order to solve for the dynamics of the problem. So imagine for linear air resistance, I have a ball that's falling under gravity subject to linear drag, and I'd like to know what its trajectory is. So this is, I guess, the free body diagram for it. So I've got um, a gravitational force pointed downwards and a drag force repelling the motion of the velocity. And if I were to balance the gravitational and drag forces, I end up with a terminal velocity. So this is just mg divided by this coefficient b. And so I can write down my equation of motion. So my double dot or mv dot is equal to mg minus bv. And so let me rearrange my terms just a little bit. And I'm going to pull out the terms that just have v and rearrange the constants. So I end up with dv by dt. I'm going to divide through by m and pull out the b. So it is going to be equal to minus b over m times this thing, so velocity, minus mg divided by b. And that's just the terminal velocity. So this is what my equation looks like. So now I can do a quick change of variables and just call this v minus v term u. So I end up with a differential equation that is du by dt is equal to minus b over m times u. And I can turn this is a separable equation, as we talked about before, and I can just really easily integrate this. I can pull the u terms to one side and the t terms to the other side. So I end up with an integral of du over u is equal to the integral from minus b over m dt prime. So this is from 0 to t, and this is from u of 0 to u of t. And we can plug in velocity afterwards. So this tells me that I have the natural log of u of t over u of 0 is equal to minus b over m times t. And so I can take the exponential of this and I end up, and I'm going to plug back in my velocities again. So I end up with so v of t minus my terminal velocity is equal to v naught minus my terminal velocity times e to the minus b over m times t. And I can integrate this once more if I cared about the trajectory, the actual trajectory. But briefly, we can just sort of sketch what this thing looks like. So we have a component here. So this is exponential decay, and then this is just a constant. So I have exponential decay that starts at this speed here and ends at my terminal velocity. So let me draw a little sketch of that. So I've got my v term here and my v naught here. And so what this is it starts at v naught and exponentially decays down to my terminal velocity. And if anyone has been skydiving, that is primarily what you would have felt. In this example, we have a droplet moving horizontally that is subjected only to quadratic drag, and we'd like to figure out what its trajectory is. So here we have our equation of motion. So we've got mx double dot, or equivalently mv dot, is equal to minus cv squared. So this is our drag term. And you'll notice that this is, again, a separable differential equation. So let me group terms and then we can integrate. So we have minus m over c times dv divided by v squared is equal to dt. And so we can integrate this from v naught to v of t, and integrate this from 0 to t. So this gives us an equation for velocity. So we have minus m over c. The minus sign is going to cancel with the integral of the 1 over v squared. So I'm going to change this to a plus sign, and the integral of 1 over v squared. So that's minus 1 over v. So I end up with 1 over v of t minus 1 over v naught is equal to time. So I can rearrange all of this, which gives me a velocity function that looks like v of t is equal to v naught divided by 1 plus t divided by m over c. So that's m over c is now a time scale. And again, we can integrate this once more if we'd like to find the x trajectory. So our x trajectory is going to be x of t is equal to x naught plus v naught. I'm going to call this time scale here tau. So v naught times tau times the log of 1 plus t over tau. So we can see what this looks like. So if I were to plot my velocity, so I start at some v naught, and as t increases, I'm going to decay away to 0, but not nearly as fast as the exponential decay that we saw in linear drag. The position, on the other hand, so imagine I'm starting at position is equal to 0. I have basically some constant piece. So this is whatever my starting position is, so 0. And then I have logarithmic growth. So I will, over very, very long times, eventually reach infinitely far away. But it will happen logarithmically slowly. So the last thing I wanted to mention very briefly is what happens with drag in 2D. So here's my generic equation. So this is quadratic drag, but it doesn't have to be quadratic drag. It could be linear drag. The only important thing is that it does depend on some speed and some direction. So in this case, we'll notice that we can rewrite the magnitude of the velocity times v hat. This is just our velocity vector. So this whole piece here is going to be equal to c times the magnitude of the velocity times the velocity vector itself. And now I can split this up into components. So I have an x term here, so vx component that depends on the magnitude of my total velocity and vx. So I can write this as minus c times the square root of vx squared plus vy squared times vx. And then my y component has gravity, but it also has an equivalent term in it. So this is going to be equal to mg minus c times, again, the magnitude of v, so this is vx squared, plus vy squared times vy. And so this equation here this is a nasty equation. So this is a set of equations for Vx and Vy, so two equations, but they both depend nonlinearly on Vx and Vy. And so this is going to call on us to need to solve numerical equations for this. And we will talk a little bit about that next week.